Good stuff. Well, hi and good afternoon to everybody. Thanks for taking the time to join us for the first session of a four-part series of the Knowledge Zone. In the past, we've run these with a focus on one code clause and then sort of closely aligned with Clima products and systems. So what is it? What's different about it this year? It's independent experts and typically two code clauses. So what I find interesting is this morning on the radio, Chris Pink talked about a 50% liability for designers and 50% on builders for poor quality buildings. And now it's a made up number from what I can gather at this point, but all liability will not land on council as the last man standing. And what does that mean in this context today? I think it's a great reminder of the need to understand more of the implications of materials or systems choices when designing. And it's a weird conundrum that compliance within an acceptable solution, and a good example is G4AS1, in that case, compliance with that acceptable solution, it doesn't guarantee compliance with at least 6 other connected clauses. So we're obviously, none of us are deliberately creating poor quality buildings, but my hope is that from these sessions, we will all take away a better understanding of how to design out poor quality outcomes through knowledge and understanding of clauses. And on top of that, the tools that can help us check and check prior to construction. So I'm now absolutely convinced that the building code is not the problem. So many people we hear complaining about the building code being inadequate may just have insufficient knowledge about what the building code really says, and then what alternative and acceptable solutions there are. Well, those are the areas that seem to be often inadequate. So the purpose and direction of these 4 webinars is about understanding not just one code clause in isolation, but 2 code clauses together, how they work, where they fit, how they fit together. So of course, it's not just about knowledge. This should affect how you design, how you write an alternative solution compliance pathway, maybe what you see in a consent when it lands on your desk. So I trust today will help you to create better buildings. It's my privilege to welcome Robyn Ryan today to discuss the clauses H1 energy efficiency and B1 structure. Just a reminder, tomorrow's session will be Dr. Anthony Pelosi from Victoria University talking about B2 durability and G4 ventilation. On Thursday, Rob Campion, our window champion, is releasing research on recessed windows in his discussion on E2 external moisture and H1 energy efficiency. And then next week, Thursday, we'll wrap up with Jason Quinn tearing apart E3 internal moisture and G4 ventilation. So we only have 1,000 seats available on this webinar platform, and Rob's session is exactly 2/3 full right now. So if you know people who need to know, they should get in fairly quickly. Hopefully that's a fear of missing out challenge there. These sessions are also being recorded and will be available on Clima's YouTube channel. Today's session will be a little bit interactive between me and Robyn, and you can also add questions using the question tab. And you'll find this in the control panel on your screen. One of our team in the background is going to collate these questions and pick out the hardest questions for us to ask Robyn during and at the end of her presentation. So let me introduce Robyn. Robyn studied as a structural engineer and now works for Oculus Building Science and Facades as a building enclosure and facade engineer. Robyn, you recently received your CPeng. That's a big deal. Tell us, was your professional interview an interview or was it more of a grilling?
Definitely not a grilling. No, it was a very cordial interview, and I think you know, they're there to assess your competence, but also just to check that you're not an AI bot who's dreamed up some creative answers to their online form. So no, it was very good.
Well, hey, let me ask you a question and I'll set you off on your presentation to us. And just a reminder to our audience, I'm going to interrupt a little bit during this with some questions just as we go. So Robyn, on the building.govt.nz website, our code clauses sit side by side and they even reference each other, but they don't get designed side by side quite often, or even by the same people. How hard is it going to be? How hard is it to change this?
You've almost taken my first slide right out of my presentation. I think it's actually really easy. It's very small tweaks that we need to make. Very small jump in knowledge, but it needs to be across the board. So yeah, once we've got a really good knowledge base from engineers, architects, mechanical engineers, quantity surveyors, subcontractors, contractors, if everybody in our industry understands these fundamentals, then some of that collaboration between designers and breaking down the barriers between these code clauses will be very easy to achieve.
Well, Robyn, the stage is yours. I'm going to turn my camera off and get out the way, and all yours.
Thanks, John. Cool. Well, I'm not going to waste any time because we've got a lot to cover. I've got way too much to shove into a 40-minute presentation, so I'm hoping that John will come back and keep me on track when I get too far off topic. But yeah, as you said, we're covering B1 structure and H1 energy efficiency. And I'm also going to shoehorn E3, a little bit of E3 internal moisture in there because it's relevant to both of those around the confluence of the topic is thermal bridging. Cool, so as I said, first slide, stolen by John, the status quo in our industry is that we're all working in silos. Where currently, early stage design decisions are dealt with in resource consent stages, where you might not have a lot of focus on energy efficiency. The structural engineer, maybe the architect are involved only, and they get to, outline where the building's going to sit in terms of distance to boundaries and height relative to the limits on that section. And then we get to detailed design stage. We add in all these complex systems and components that we need to make a building do what it, keep us safe, warm and dry and comfortable. And then we try and see what gaps are left at the end and we can shove some insulation in. So instead, what I propose we need to do is really get to thinking about thermal efficiency early in that design phase so that things don't get baked into those resource consent or early stage design renders that we can't then undo. So structural engineers and architects need to consider where the insulation is going to go when they're doing these initial setouts. And yeah, keeping in mind that our roof design also needs to potentially allow for an insulation layer above our structure. So just quickly summarizing where we're at with B1 structure, the building code itself has these, it's of course the performance-based building code. The ultimate goal or objective is to keep people and property safe. The performance-based building code has these broad statements that explain what a building must do, but the code doesn't really provide any detail on how we should design or build them. That level of detail has been provided in the acceptable solutions and the verification methods. For B1, the most common ones are B1 AS1 and B1 VM1. So within B1 AS1 sits 3604, so that's the really common timber framing, light timber framing structure standard. And then under B1 VM1, you might get a concrete, steel, or structural timber, more bigger timber sitting under that verification method. Now, we also need to remember that we always have the alternative solutions sitting next to verification methods and acceptable solutions. So that's highlighted in pink on the left-hand side here. And that would be common, for example, with mass timber design or based isolated structures. They are currently not covered by any of our alternative, our acceptable solutions or verification methods. And these alternative solutions exist for showing compliance to all code clauses. So the same applies to H1. We've got our overall goal or objective is to facilitate the efficient use of energy. Under that, we have our acceptable solutions, under which encompasses both the schedule method, which is getting phased out at the end of this year, and the calculation method, which is slightly more flexible but still somewhat limited. Then we have our verification methods, and they're commonly termed the modelling methods. Again, we have alternative solutions that are possible and sit alongside those compliance pathways. Now I've got a little note there, my last slide. Note that none of the methods of H1 compliance will actually tell you how much energy a building will use. They're only really useful as a comparative tool. And it says that explicitly in H1VM1. The results of thermal modelling should not be construed as a guarantee of the actual energy use of the building. So they're really quite, quite plainly stating that this is a box ticking exercise and will not be in any way reflective of your power bill at the end of the day. H1 also allows designers to manipulate or game the model. So you can theoretically make the reference building worse to make your design look better and therefore compliant. It also allows all sorts of thermal bridging, depending on your interpretation of some wording. And the kicker for me is that H1 acceptable solutions and verification methods all seem to ignore the fundamentals of efficient design, starting with form factor. So is our building envelope sensible shape, or is it too spread out with lots of area for heat to escape from? Are we sensibly orientating that building on the site to minimize excessive solar gains and prevent overheating? And it also completely ignores air tightness and the effect that that has on energy efficiency and indoor air quality of the building. And one last thing that H1 does not do is that it doesn't cover off E3 internal condensation. So to John's introduction point, by ticking the box of H1, we can't assume that we've ticked our E3 box. We might need to be coming back and adding more insulation to achieve internal moisture control. So that's our status quo. Where are we headed? So New Zealand has signed up for net zero emissions by 2050. That applies to the construction industry, and we've got kind of to balance two parts of that, both the embodied carbon, so the amount of carbon that's built in to a structure at the start of its lifetime. That sits probably best under the B1 topic of this presentation. And then we've got operational efficiency, so all of the energy use that that building will have over the lifetime of that building, and that's sitting more under the H1 part of this topic. So under the operational efficiency, the Building for Climate Change program that MB has presented actually has targets to reduce our thermal performance demand in a series of stages. We've got an initial cap, an intermediate cap, and a final cap. Now they've listed the final cap in 2035, so only 10 years away, and that number that I've highlighted there, 15, is actually the same as the performance target for a passive house classic design in New Zealand at the moment. So it's a pretty ambitious target, I think, for 10 years. It's fantastic to see, but it really indicates that the direction that we're going, we need to really be making massive improvements in the efficiency of our buildings. And that approach can become problematic with our common, status quo design approach of just shoving insulation in at the end, both from an energy efficiency perspective, but also from a moisture control perspective and a durability perspective. We've got, more modern buildings are more airtight. There's often not enough or adequate ventilation provided. And we've also got a compounding factor that less heat is escaping from our buildings because of this extra efficiencies that we're designing in. And that heat has, in the past, allowed us to get away with some bad design decisions where moisture would accumulate and then the heat would dry it out. If we've reduced our energy loss across the thermal boundary, then we're reducing that ability for our buildings to kind of buffer themselves and fix the mistakes that we've put in. So yeah, that approach that we're currently heading down only can get us so far. If we're going to achieve these big targets that we've got, especially by 2035, then we need to start taking a step back and thinking, at an earlier stage about holistic design. So ways I think we can do that, again, is lifting the knowledge across the board. As I said earlier, I think, you know, we've got disciplines right the way across the mechanical engineering, architectural, structural engineers, quantity surveyors. They all need to understand these fundamentals so that those early stage design decisions are appropriately geared and setting us up for success. And good, you've jumped in here, John. We're gonna use some of the tools where our building code might be lacking in the guidance that we have. You know, we need to start thinking about what experience that our international colleagues have in this high efficient design stage.
So, Robyn, I think it is a good time to jump in with the first question, and it came actually probably during my introduction, which I can understand, and this is really what this discussion is about. So the question that came through is, how can you say there is no problem with the building code and it's the industry understanding that is the problem, where there is no code requirement for airtightness or proper ventilation, recessed windows, etc., etc.? Do you want to give that a crack at responding?
Yeah, absolutely. I think what are we talking about when we talk about the code? Are we talking about the acceptable solutions and the verification methods, which are one compliance pathway to achieving that code? Or are we talking about the actual performance-based statements, which are very, you know, broad-reaching, and they, yeah, I think it's a fair point. I can understand the designer's perspective here in that question. There's not enough detail provided in our code, but that's by design. That, you know, people who created this building code were trying to give us freedom to make design decisions, but ultimately that means we're left with a lack of detail in things like, you know, air tightness targets. So while I appreciate that point, I think if you were working to the actual objectives of the building code, then you would you know, via maybe an alternative solution, then that would not be a fair statement. But if you're working within the verification methods and those acceptable solutions, then yeah, fair point. There's not enough detail on how we can get there with our performance.
Yeah, so I think, yeah, my view on that and my statement at the beginning too is that we need to lift our eyes above what we're doing and look back at the higher level objectives of the code clauses, and that is challenging to stay kind of at that level. And then you've got to sort of balance that, you've got those higher level aspirational targets of, you know, the 2035 approach as well.
Yeah, like, you know, back to the objectives, the goal of H1 energy efficiency: facilitate the efficient use of energy. There's nothing in there about
so go for it. Yeah. Right. Hey, I've got one quick question for you, which it's just a short one just to add in here. So when doing a small additional alteration with, will the schedule method still be available, or will you need to calculate the whole of the existing, even if it's unknown? Is it?
Oh,
we don't need to answer it. If you don't know, that's fine. We'll just keep on cracking.
I think that all the status quo of you know, that the part that you're renovating needs to be meeting code still applies, and so whether you do that via the schedule method, the acceptable solution, sorry, the schedule method calculation or modelling, if one of those gets taken away from you, you'll still have to meet compliance via the other pathways for that portion, for the renovated portion.
Cool. I'll jump out the way again and let you crack on.
Cool. Okay, thanks. So I think I've talked enough about fundamentals, and we've got to get into some physics. So thermal bridging, as I say, I think that's really the confluence of these two topics, structure and energy efficiency. A thermal bridge is where our layer of thermal insulation is interrupted. It relies on the concept of heat transfer via conduction. So if you look at this little diagram, it's that person's hand getting burnt by the pot handle as the pot handle warms up. So in an ideal world, our insulation layer would be continuous, completely continuous, not interrupted by anything, and would be outside of the structure to minimize the heat fluctuations and the moisture fluctuations that our structure needs to undergo. And that leads into durability. So what's the problem with thermal bridging? The impact is, it's not a very new concept, but it's completely overlooked because it's very easy to underestimate. It's supposedly hard to calculate. We can show you how to calculate that later on in the presentation. There's previously been a lack of data available. Again, I'm going to show you where to find the data during the presentation. It can be difficult to mitigate thermal bridges once you know you've got them. And the kicker for me, mitigation is not specifically required by our H1, AS1, H1, VM1, acceptable solutions and verification methods. I think the wording in there is that you have to consider thermal bridging. But once you've had, a few minutes of consideration, you can move on with absolutely no changes to your design. So yeah, I think we don't have a good framework for solving thermal bridges in our acceptable solutions and verification methods yet. So why should we care then? Well, we've got ultimately that goal of improving our thermal efficiency so that we can use less energy. We also want to reduce our risk of condensation and mold growth, and I'll dive into this a little bit later on, and also improving thermal comfort. Now, this is often quite a hard sell in a design table for a commercial building or institutional building. But when we talk about our homes and designing our homes to be comfortable, I think that really hits home for people. Thermal bridges create spots where heat can escape or enters more rapidly, leading to those zones being colder. So if you're sitting between something like a window and the heater in the middle of your room or office, your body is radiating more heat towards that window and less heat towards the warm interior. And so it leaves you feeling quite unbalanced and therefore uncomfortable. So if we can mitigate those thermal bridges, reduce those cold spots, then we feel much more comfortable in our homes, offices, institutions. Now, I think key to this discussion is realizing the differences in the material properties that we commonly work with. So right at the top there, I want you guys to all remember this number when you go home. Steel has a massive thermal conductivity of 50 watts per meter Kelvin. Now, if you compare that to something like timber, which is in the decimal places, or insulation, again, 0.04, that number, that 50 number is huge. Aluminium, again, that's off the charts, and you can see why there's been such a push lately towards thermally breaking our aluminium window frames. So yeah, the key thing to keep in mind here is the relative difference between these materials, so that we can better understand which of our thermal bridges are going to have more of an impact, and we can focus our efforts on mitigating those ones. Another concept to keep in mind, heat flows in 3D. So whenever you're working with U values or R values, you need to keep in mind that these rely on assumptions of 1D heat flow, which is accurate if your assembly is consistent, like if you're between areas of your stud and you've got a nice chunk of, batt insulation there. You've got even heat flow across all of those layers. But as we get closer and closer to the studs, if they were steel or even timber, we're going to have this heat flowing in 3D around those different elements. And you can see here an illustration of that nice colourful picture on the left-hand side shows if you've got a steel column within the depth of your wall and you've got insulation on either side of it. The heat, the temperature of the steel on the interior side of that steel is essentially the same temperature as it is on the outside. That insulation on either side of it is not doing anything really to change the temperature of that steel. So by the time you reach the gypsum board on the interior side of the steel, those temperatures are around 8 degrees, even lower, and that gives you that risk of condensation. So you can see on the right-hand side, that picture shows it really well. If you had a steel stud, you've got risk of moisture accumulating on that side, and therefore potential for mold growth in those areas. So we get those, those common strips of EPS to thermally break steel studs on the outside of the framing, but we need to think about, okay, those strips need to be at least a little bit wider than the steel stud to effectively mitigate that heat flowing around the corners, and ideally it would be continuous right the way across that layer, before you, between the sheathing or cladding and your steel. Because if we think in 3D, let's take a step back and think about it, the last building site that we were all on. There's not many instances where you don't have a junction, a corner, a bottom plate, a top plate, a deflection head. All of these things, our buildings are very complex in geometry, and so we can't keep thinking in 1D, and that's where the benefits of that continuous external insulation come in. All right, so as I said at the start, we're going to touch on internal moisture, E3 as well, because it's so related here. So going back to the code clause, again, our goal or objective is to safeguard people against illness, injury, or loss of immunity that could result from the accumulation of internal moisture. And then we step through into the functional requirement. Buildings must be constructed to avoid the likelihood of fungal growth or the accumulation of contaminants on linings and other building elements. So that's actually fantastic in my opinion. I think E3 as a code clause is awesome, but unfortunately it really again starts to break down when we reach the acceptable solution. There's such limited guidance around a key thing like thermal bridging, and it's led to a lot of confusion in our industry. Sorry, I have to take a little pause. I'm 7 months pregnant and puffing and panting my way through this presentation. You have to excuse me. Recently had an example. I'll just jump to the next slide actually. We define thermal bridging in three different ways. It's the same thermal bridging, but this is just the name. These are just the names that we give them. So if you can, if you're dealing with an area, so a wall or a roof where you've got a regular interrupting structural member like a steel stud or a timber stud, those types of thermal bridges can often be dealt with in the U value or the R value, and so we call those 1D or an area thermal bridge. The next one along is a line, so a 2D thermal bridge, for example, a slab edge or a mid-floor in a multi-story building. And then a 3D is a point thermal bridge, so an example there like a steel beam that's penetrating out through the thermal envelope. So that example that I was about to start earlier, we had a project come across my desk where the structure, the roof structure, had these steel beams that were supporting a canopy that wrapped around the house, all the way around the outside of the house. And in consent, building consent officer correctly pointed out that there was a lot of thermal bridging going on, and therefore a high risk of condensation problems at the points where these beams penetrated through. But unfortunately, they referenced that clause in the acceptable solution. Just back a slide here, and it's talking about steel framing. Now, that is talking about steel framing and a thermal break that can sit on the outside of a steel framing element is only really relevant for steel that's in the plane of the roof or the wall assembly. Once you get into a 3D situation where the thermal bridge is going through the thermal envelope, we need to be talking about a whole different set of tools and mitigation methods. We can't put 10 mil strip of EPS around that steel beam and say that the problem is fixed. So yeah, that's a really good example of how our code, or the detail that's provided in our acceptable solutions and verification methods is causing confusion, because there's not really the fundamental science direction given. So we need to look elsewhere. We need to be thinking alternative solutions, international guidance on how we can mitigate these thermal bridges. Do you want to jump in there, John?
Quick question. Yeah, can you just spend a moment with the 1D area, because it looks from your diagram there like it would be easy to see that as a line, because it's one piece of steel. You just want to describe how you differentiate between those two?
Yeah, sure. I think it's you're absolutely right, and the concept of thermal bridging still applies across these different definitions. It's just the way that we term them and deal with them in energy models. So, for example, in a wall or a roof, we have studs at 400 centers or purlins at 900 centers. Those are repeating elements, and we can predict and estimate those and average the effect of those thermal bridges into our U value or our R value. So that's a nice simple way that we can account for those, what they are, as you say, line thermal bridges, but we can bake them in to our R values.
Okay, across an area. And then just really briefly on that, then with that diagram on the left, the best way of dealing with that wall with steel frame, because the steel frame's not the problem, right? The material isn't the problem, it's how we've dealt with it. So how do you deal with that?
So the best way to deal with steel framing thermal bridging is to have a continuous layer of external insulation sitting outboard of that steel framing. So that means it's going to go right across your building paper or your cladding line, and it's going to be continuous. There will be no interruptions, and no ability for that heat loss to escape.
Right, cool. Excellent. Jump out.
Thanks, John. Okay, so if we were to look to the Passive House Standard, international experience, how can we more accurately define and therefore mitigate these thermal bridges? Well, we would use a 2D or a 3D software modeling tool, and we would be modeling to this ISO standard. And that, there's software packages out there such as Flixo and Therm in the 2D space. In the 3D space, I'm not that familiar with them, but they're all sorts of kind of finite element analysis based software tools for modeling elements in 3D. So here's an example of where a balcony is supported by steel beams that are point thermal bridges, so 3D thermal bridges. They've been modeled in a 3D software program. You can see that in the nice isothermal colorful picture in the middle. And then they've designed the thickness of the thermal break that they've put between the steel and the concrete mid-floor, and then they've designed that thickness to meet the requirements of what we call the FRSI, or the hygiene criteria. And that's just a pass or fail criteria, and that demonstrates whether you've got a risk of mold growth at that point or not. All right, so what are the fundamental concepts around designing out thermal bridging? We want to keep that in mind. That's the first step, is how can we not even have to deal with thermal bridges in the first place? It gets harder as they get further down the line of design. So external insulation is always going to be first port of call. It allows you to completely wrap the outside of your building, and as long as you can keep that continuous, you won't have any major thermal bridges to deal with. Then next best, if you had to have your insulation in between your studs or in the depth of your wall cavity, then can we offset our steel and concrete elements to be inside that line instead of within the wall or roof themselves? Third port of call, so stepping down the list of in priority of how effective these techniques are going to be. Can we rationalize timber framing wherever possible, or steel framing if you haven't thermally broken that as well? you know, can we reduce the amount of nogs, dwangs, studs that we have to be absolutely the you know, the balance between structure and energy efficiency. Some more techniques around minimizing thermal bridging. So this is when it's kind of the ambulance at the bottom of the cliff, when you can't when you can't use external insulation or all those other mitigation factors. You can wrap or thermally break steel beams that penetrate through the boundary. So you can, you know, wrap insulation around the outside of the steel beam for a certain amount of length to mitigate that heat loss. Or you can put in a structural thermal break pad between steel plates. And this has actually led to a little offshoot company that my sister and I have started. But we'll just pause the presentation here for a little plug on that. It was born out of frustration, really, for me working as a designer, that these thermal break plates are available internationally, proven track record of performance, you know, not expensive, not difficult, but there's no one supplying them here in New Zealand. So yeah, Little Thermal Innovations is the side company that my sister and I started doing thermal break plates. And then other techniques you can use, supporting balconies and you know, canopies from structure that's outside of your thermal envelope rather than cantilevering through. That's another good way. It's often quite a difficult one to achieve unless you've thought about it early in the design phase. And then Balcanto is an example of another company in New Zealand that's providing solutions here. So balconies are a common one. If you've got a concrete slab that's cantilevering out, that concrete slab is a lined thermal bridge. So can we instead minimize the effect of that thermal bridge by breaking it up, separating it into steel beams that are supported at just points? So we've minimized the amount of area where the thermal bridging occurs, and then we can also add in thermal break plates to break those points of weakness. All right, now John, I hope you're going to come online here because I've got some good, I want some discussion here. We've been badgering on about this for a long time at Oculus, so I've got a link at the bottom of my page, and I think someone's going to put it in the chat there, a blog post written by Sean, my boss, and it really lays out the case. You know, what do we need NOGs for? If you're working in the 3604 realm of design, so single family home or, you know, low rise timber frame construction, there's this clause and lateral support of studs. And it gives you these options. You either need an exterior wall cladding that complies with E2AS1 or an interior wall lining that's on board, I think 10 mil is sufficient to provide lateral support of studs. Go with dwangs or nogs. Now, so that's an either or. You do not need both. And we've been arguing for a long time to try and minimize the number of, you know, the amount of timber in our walls, because if you've got more timber, then you've therefore got less insulation. So a lot of buildings we've got working outside of the 3604 realm, we have timber frame walls that are infill. So if it's just a concrete slab, so, you know, and the infill wall is just spanning between slabs, then again, you really don't need NOGs to be providing any structural purpose. So they're really just taking up space, you know, eating into our carbon budget. And we get a lot of resistance still from engineers, builders, architects who want to fix interior, you know, fixtures too. I think we can solve all of these problems. Let's take them one by one, John. What are some of the common reasons that people want to have NOGs in their timber frame walls still?
Yeah, that's a toughie. Maybe one of them is we've just always done it like that, therefore we must need it. I don't know. Does that sound?
Yeah. I think so, and I've actually heard cases of, you know, where the wall was designed without NOGs, but then the pre-nail truss guy put in NOGs because he didn't feel comfortable sending out a frame without NOGs, and then they had to rip them out when they got those timber frames to site. So an exorbitant amount of waste when we're talking about how we can make construction cheaper.
And I think in terms of the solutions for that, it's not just your second to last point there, or your last actual point. Interior fixtures can be fixed to nogs on the flat. That's fine, but then what about the external battens that you've got there as well? What about that on the inside, so an internal service cavity approach, where your 45 running horizontally is creating that lateral support as well? So I think there's got to be other ways. What about solid sheathing, continuous sheathing on the outside or on the inside? Suddenly your nogs are superfluous, and you've got space for more insulation.
Yeah, absolutely. Yeah, and a common one we also get is, we need them for the cladding. The cladding needs, it's vertical cladding, so therefore we need the horizontals to fix the battens to. But you can just use a structural batten on the outside, so that can either be a metal castellated batten or a timber one. I think timber ones need to be a bit thicker, so they'd be in the 45mm brown. But yeah, there's options there. So, but yeah, if there's any other questions in the chat about why we should have nogs or dwangs, sorry for the South Islanders, would love to hear them.
And we had sorry, Robyn, and for that we will drop that link to Sean's article and either the questions or the chat. Sorry, I don't know which one it's going to go into. Right.
No, thanks. Then this is the big one. I got a little bit despondent about this recently, having had the battle in the design room at the design meetings, managed to convince everyone that we didn't need nogs, and then got to site and we see things like this all the time. That picture is taken from one of our construction sites, and I want to tell you now, I've counted them. There's 14 studs next to that window jamb. 14. I have no idea why, and I cannot rationalize what you would need 14 studs for. But all I know is that there is, we have lost an opportunity to insulate that wall properly. Beacon Pathways study recently found, not that recently, actually a few years ago now, found an average of 34% timber in our typical walls, whereas H1 calculations are more sitting around the average of 14 to 18%. So we're massively overestimating the thermal performance of our wall there. In the MB consultation paper that came out more recently, they released data from placemakers who have looked at their manufacturing records of pre-nailed frames, and out of 452 buildings, they found an average of 38% of timber. So we, in that consultation paper, actually proposes lowering our R values of our assumed, wall values to be in line with those numbers. So there's, a bit of a weird logic there, but I think acceptance is the first step to solving the problem. Here's another example. I just felt terrible when I saw this. I don't know, I haven't actually done the numbers, but I reckon the framing ratio on that shop drawing is probably around the 70% mark. And so, this is demonstrating this is not just cowboys on site or conservative builders chucking in a few extra nogs or studs. This is built into our design process, and the assumptions in the H1 report definitely did not reflect what this shop drawing showed. All right, so somebody's going to chuck the link to this fantastic document into the chat. I hope everybody in this webinar has heard of this, or is at least now going to go and have a look at it after this. But this is a handbook that was put together between Brands and Fins, so Passive House Institute of New Zealand, done by Jason Quinn and his fantastic team at Sustainable Engineering, and they have gone through a whole lot of typical New Zealand construction details, and they've modeled them with those software tools that I referred to earlier, so that we've got the data available to deal with thermal bridging. So now we can take these numbers, they are sitting there with a range of insulation and thicknesses of studs usually, and you can look through this book, find what's most appropriate for your building or your detail. It's not always going to be perfect, but there's a starting point there for being able to know how much heat loss is going to occur at that junction, and being able to quantify whether your FRSI or your hygiene criteria is met. What's the risk of mold growth or internal condensation at that junction? All right, and then last thing I wanted to talk about was some of these exterior insulation and warm roof assembly things that I've mentioned. I know they won't be commonplace for some people in the webinar, so how can we, if you've never done exterior insulation, where's your first port of call? So this is, here's an example, a photo showing a rock wool exterior insulation. So there's a couple of different options out there, but rock wool is a fantastic product because it's non-combustible. So it can be used for all different heights and risk levels for reducing that fire risk in the cladding cavity. Another example of an exterior insulation is PIR. So that's polyisocyanurate, a rigid foam insulation, and that is also suitable, but there's a fire risk associated with that one. So it's more limited to the lower below 10 metre buildings. And this photo also shows you how you can attach your cladding to that, like once you've got your insulation on the outside, how do you then attach the cladding over the top of it? There's this whole lot of different systems out there. Outright is a really good company to look at. They've got a whole different range of solutions. I think Roof Logic also do a system for external insulation. I mean, there's a number of different companies that will be kicking me after this for not having mentioned their names, but those are the two that spring to my mind. And yeah, lots of different systems, and they can be applied to any cladding type that I've ever heard of. To date, don't know of any cladding systems where you can't use external insulation, including brick. So yeah, there are clip systems that can allow for brick to be put on the outside of an external insulation system. Warm roofs, again, suppliers like Roof Logic, Neuralite, Diamond have their own system. They all have continuous insulation outboard of the main structural roof. And one of the key things that I think when you're specifying or suggesting one of these types of warm roofs or warm walls in the design phase is to be ready and waiting for the kickback that you will get from someone further down the track, usually a cost consideration. So, typically we get very, I would say, conservative or risk-averse cost estimations for these systems because they're lesser known in the industry. So we need to be ready and waiting for these arguments to come through. Look, ask for the data, make sure they're comparing apples with apples. So if you're talking about a warm roof, has the cold roof that they're comparing it to per square metre, has that adequately dealt with interior moisture condensation risk? Is there a vapor control layer detailed at the ceiling line? Has that been sealed around every single penetration sprinkler head that you're going to have to do? Has that labour factor been added to the cost as well? I think, yeah, when we compare these solutions with the alternatives, we need to be making sure that we're comparing apples with apples. All right, so yeah, how are we going to get to the end point that we started out with? That net zero 2050 seems like a very tricky target, especially in the current market. With a lot of projects struggling for funding, there's a lot of hurt out in the industry at the moment. So arguing for perceived higher cost solutions can be a really hard sell at the moment. But we need to, taking into account what John said from Chris Pink this morning, the onus on the designers and the people working in the industry. We're getting to know more and more about the building science behind these fundamentals. And so our window of opportunity to continue on with our status quo is quickly shrinking. We need to be thinking about holistic design. We need everyone in the industry to be to know this stuff so that we can have, you know, good robust discussions about the relative costs between these items. And key factor to take away from today, if you remember nothing else, is early design decisions matter. So when you're doing your beam and your column set outs or your roof line, keep in mind, where is the insulation going to go relative to this structure? All right, John, I think I've definitely gone over time there. Do you want to let me know what kind of questions we've got?
Yeah, no, that's good. No, we've got about 9 minutes before we need to finish. But just going back to your external insulation image there, we had a question prior to you having that on screen, but it's still a good one. If you used something like a horizontal Z girt, is that going to be a bad thermal bridge? I mean, the answer is, well, yes, if it's a solid steel girt, but we've got options, and that I mean, maybe you answer that, and maybe I'll add something to that if need be as well.
Yeah, so you're absolutely right. If you're using a Z-girt that goes from the start of the insulation to the outside of insulation, then it is a thermal bridge, but you can also provide a little thermal break pad. So I think Roof Logic system has some plastic packers in behind those horizontal battens, and that provides that thermal break. Or like this system that I'm showing is a fiberglass product. It's out of Canada. It's called Cascadia Clips, and they are, again, you know, essentially a thermal break.
All right. Question: how can we work and collaborate on research and development fronts of H1 with you? And this is coming from doctoral researchers. Is there space for collaboration?
Absolutely. Oh, there's so many research topics I am dying to get into. I can't wait to get back into university and do some research. But if there's people out there who want to study something, yeah, absolutely get in touch with us. Or you know, John, you've done a master's degree. I'm sure you'd be a great sounding board for future research topics in this space.
Yep, happy to be involved somehow in there. That'd be great. Okay, Robyn, what do you think about removing all acceptable solutions from the building code? Wouldn't that remove the risk of using the building code as a design manual? And then a qualification on that. I know it might be overreaching.
Yeah, I mean, I think we've got a huge challenge ahead, and all options should be considered. You would need a little bit of time to think that one through, I think, before I could put my strong opinion behind it either way.
Cool. All right. Is there a goal to require actual ventilation at some point? Natural ventilation appears to be a myth, as people don't want to open windows when the heat is on. This leads to sick building syndrome, crying windows, and mold.
Key one there, mechanical ventilation with heat recovery. That is the answer. It's not going to work in every situation, but ultimately I think that's the one piece of kit that we can solve majority of our ventilation woes with. So for anyone that doesn't know, that's a ventilation system that's balanced, so it's allowing the same amount of air in as out. So it's taking all of the fresh air in and tempering that air with the external air. So as it goes through a heat exchanger, all of the waste heat from the extract is going into the incoming air. So you've got a much more efficient system. You've got a very good amount of fresh air coming in, but it's not going to eat up into your power bill at the end of the day. Now, these systems are typically, you know, seen to be expensive in the market, but again, just the same as a thermally broken aluminium frame was seen to be expensive until recently. These changes, you know, as soon as we make the change, the industry catches up, the prices drop, becomes more standard, and you know, all of the installation know-how is already there in the passive house community.
All right, going way back into your presentation now, which is fine. Does the minimum thermal break of 10 millimeters of an XPS strip at R 0.25 actually mitigate against condensation in a steel framed wall? Yeah, that's the end of the question. So does it actually mitigate? Does it make the difference? Can it make any difference?
It can make a difference. It depends what you are measuring it against. If you did a Flexo model like one of these, and you measured the FRSI number, so that's the pass-fail criteria around condensation risk, and it depends on your climate and your interior conditions. So how much humidity is in the room, what is the temperature, what's the relative humidity of the external air, and the occupancy of the space, obviously, the number of people in there that are heating, cooking, doing their washing, those factors all come into it. So I can't give you a yes or no on that.
Well, it sounds like a very engineering response. It depends. But let me put it to you another way. If you had opportunity, or if you were building like this for your own home with your family, would you put XPS strips of 0.25 outside your steel studs on your framed wall?
No.
Okay, thank you. I hope that was an adequate answer to that person's question. Who is providing the PHPP service? So that's the Passive House Planning Package service as a provider, and what are the best details available to integrate high performance with the building code? Let's deal with the first one first. So who's offering PHPP modeling as a service?
So anyone who's a passive house designer would be using PHPP software. There might be others out there. You know, I know that our company uses PHPP as a modeling tool as well for non-passive houses. It's a really good tool for energy modeling because it's predictive. So unlike our H1 modeling methods, which are comparative only and you like kind of fictitious, PHPP gives you an actual estimated energy demand for if you were to heat and cool your building between certain boundary conditions. And sorry, what was the second part of that question?
The second part is what is the best detail available to integrate high performance to the building code, especially air tightness and surface cavities? Oh, okay, so this is a question around how to get bracing into a wall where you've got air tightness and surface cavities. So maybe where does somebody go to get good details on that? I might just answer that and say we've got plenty on our website, on the ProClima website, and that's what we do in terms of creating air tightness and then offering, you know, the how to do that, how to get bracing around that. Robyn, any other options that you can think of around that?
I mean, there's fantastic structural engineers out there. Damien McGill in Christchurch, EZ Paula Huggins in Queenstown, lots of structural engineers out there who understand the fundamentals of passive house design and apply those to structural solutions as well.
Great. And then let's just go the last one here. Oh no, sorry, that's a repeat of the horizontal girt. Sorry, that's come up twice accidentally. All right, let's do the next one. So what tools are available in New Zealand while designing around thermal bridging, particularly when it comes to building concrete walls? So what tools would be applicable?
Fantastic reference in here. So back to the construction details handbook, there's some concrete slab edge details in there that you can start with. If you had concrete like precast panels in your wall, then I'd recommend starting to look at like a concrete sandwich panel. So that's allowing a continuous layer of insulation to be sandwiched in between two bits of concrete. So usually the interior is, you know, your typical 150 or 200 mil thick precast concrete. You'd have maybe 50 mils of rigid insulation and then a 50 mil thick wide of concrete on the outside, and they're connected together with some clever clips. And there's a precast yard in Auckland that I know has made these for a recent project. So yeah, the solutions are there and being made in New Zealand. So it's not you know, it's not too far away from reality.
Great. Well, Robyn, hey, thank you so much for your presentation. I know there's a string more questions that are sitting waiting that we haven't got time for. There's a bunch of questions and statements, both for and, well, not just against the whole NOG thing, but just asking for more clarity. So that's a good push there to go and read that article for a start, and maybe get in touch with you before you go on maternity leave to get some responses there on the NOGs thing. So look,
Yeah.
I hope everyone has enjoyed this session, has been challenged across this lunchtime. A huge thank you to Robyn and the Oculus Building Science and Facades team. I look forward to our presentation tomorrow from Dr. Anthony Pelosi on G4 and B2. So thank you so much for being part of today's session. See you later.
Thanks, John.